Okay, continuing with complexity, we'll look at manifestations of complexity and also how disproportionately the causes can drive impacts. There are amplifications possible in a complex system of a small perturbation, which is always something to watch out for. In terms of manifestations of complexity, whilst the constitution of complexity itself is arguably relatively straightforward, that is, many elements with rich dynamic and non-linear interactions, the manifestations of such complexity are indeed striking, with far-reaching significance for all of us, which is what we have in terms of CO2 being a trace gas, so its parts per million by volume compared to nitrogen and oxygen, which are massive. So that's a problem in terms of capturing it. For example, 0.04% of the atmosphere is CO2, and yet it can trap energy and create internal feedbacks which amplify things like warming and then increased water vapor, which itself is a greenhouse gas, further warming, and so on and so forth, right? I do not have room to elaborate on all the exciting contributions of complexity science. Still, I devote this section to introducing the most central manifestations of complexity for understanding, explaining, and improving our challenges for sustainability and the world. So here is a good example from the Earth system: a reinforcing feedback loop diminishing the Arctic sea ice cover. Satellite images from NASA of the minimum ice cover during 2020, so second edition, later data, compared to a 30-year average minimum over here. So you have a feedback happening where you have let's say increased greenhouse gases which have increased temperature, which melts more ice, so the albedo goes down. The ocean is much darker than sea ice cover, which means the ocean absorbs more heat, which further increases the ocean temperature, further reduces the ice cover, and so on. And these positive feedbacks can go very rapidly, as we know from past climate data. There are many such feedbacks in the Earth system, and we always have to worry about what is a positive feedback and what is a negative feedback. And when you consider everything together, is it a net negative feedback or positive feedback if we keep perturbing the greenhouse gases? For example, with global warming, the outgoing long wave radiation to space should increase because it's a black body radiation of sigma to the sigma times temperature to the fourth, where temperature is the emission temperature and sigma is the Stefan-Boltzmann constant. But we know by now that this feedback, a negative feedback, is too small compared to the rapid rates at which greenhouse gas increases cause global warming, and so on, right? So there is a disproportionality between cause and effect as well. The nonlinearity of dynamic interactions in complex systems has another fundamental effect closely linked to these feedbacks. So here we have what is called polar amplification. So if you look at the global warming map, which I have discussed in many different courses, or you can Google for it, you will see that this region is warming the fastest compared to rest of the world and rest of the oceans as well. There are some parts of Middle East and Mediterranean which are also warming fast, but this polar amplification is directly related to this ice albedo feedback, right? So these are the things we have to worry about in terms of the disproportionality between the cause and effect, between input and output. This disproportionality means that small changes sometimes cause massive effect, whilst big changes sometimes fail to generate much effect at all, and the trick is to know which one does what, right? The relationship between cause and effect may also change drastically over some input levels. So you keep pushing some things and then you may hit a threshold, and then you may have a huge amplification suddenly kicking in, which is often referred to as a threshold, a switch point, a tipping point, and so on and so forth. So the relationship between cause and effect may also change drastically over some input levels or thresholds. It is referred to as the threshold effects or tipping points, and is further addressed in a later section on the consequences of complexity. Remember the terrifying potential tipping point of the Amazon rainforest in chapter 4. In addition, the relationship between cause and effect may change over time as the complex system evolves. There may be negative feedbacks. This decoupling of input and output in terms of proportionality and performance is a central feature of complexity and cannot be found in simple or complicated systems. So here is a clear definition of complex versus complicated, the disproportionality between cause and effect. As for tipping point, as I commented before and as I've commented elsewhere and written in the media and so on, tipping points exist in the system, and we know that they have occurred in the past, related to orbital forcings. Currently, the way we are going, do we know when we are going to arrive at this tipping point of the Amazon rainforest, for example? The idea is that with global warming and deforestation, we may accelerate the situation where the entire Amazon will die off. Well, is it a possibility? Yes, in terms of non-zero probability it is, but the trick is to know if and when it will happen and whether you can predict it. And by definition, tipping points are not predictable. They just arrive on you suddenly and surprise you. So we have to be careful about, again, humility. If we don't know and the results are only provisional, then we have to be humble about it in terms of expecting people to change the system, change behaviors, invest massively into doing things that are not guaranteed to work, and so on and so forth. So there is the butterfly shape appearing when plotting the chaotic oscillation of systems between two attractors of a Lorentz system. This is the emergence of chaos. So this is 9.5, which I skipped the text, but let me explain what happens. We have, Ed Lorenz at MIT found out in the 1960s, I think, that he was trying to construct a simple model for weather with some simple equations which had nonlinear terms in them. And it's a very innocuous looking system, but he found that very small perturbations to the initial condition when integrating these equations produced very divergent solutions, which was relevant for weather. So weather is considered an initial condition problem in the sense that the atmosphere acts independently of the ocean because the ocean has high heat capacity very slowly, and on short few days of weather it doesn't change that much. So you can predict weather by assuming that atmosphere is doing everything in terms of taking the energy, producing solutions, but you have to know what the initial conditions are now. If I'm going to integrate now into the future for 6 hours, 12 hours, 24 hours, or a few days, the initial conditions are very important. And what he pointed out is that small errors in the initial conditions or small differences between observations and prescribed initial conditions can produce very divergent weather outcomes. This is called chaos, and it became a huge field of study, dynamic systems and so on. And he found that these complex systems, chaotic systems, still have some things called strange attractors, so that no matter where you are, the solutions tend to head towards one solution or the other, or one attractor or the other, which means that you can be coming along here and suddenly go in this direction or this direction. They have bifurcation points and so on and so forth, but essentially you can think of those as thresholds or tipping points and so on and so forth. And this shape also kind of evoked the metaphor that the flapping of a butterfly's wing in Brazil can produce a typhoon in the Philippines because of these non-linearities and so on and so forth. Of course, we have come a long way since, but still we know that weather is a chaotic system, so weather forecast cannot go for more than a few days. Depends on whether you are in the tropics or mid-latitudes. The systems are different, the dynamics are different, the emergence of non-linearity and the growth of the errors are very different, and so on and so forth. So that's complexity, and we'll come back and look at emergence. I think this is a long section, so I should leave this here and come back and talk about emergence in the next podcast. Okay, so the concepts are important and they are very relevant for the Earth system and will become relevant for sustainability as well, because if we take one trajectory based on the current information on risk and resilience, we may end up in a very different place as opposed to a slightly different choice, which may seemingly appear very close to each other, but cause and effect can be so decoupled that one will take you in a very different trajectory than another. So think of as two different strange attractors, but this can be a problem because you have a continuum between adaptation and maladaptation, where you are adapting to risks that are uncertain based on the current knowledge, but it may end up becoming maladaptation because of a small difference in the way you proceeded to do the adaptation. I have examples in my adaptation course that you can look up, but this is very critical to understand before we go on to learning about how to represent the human environment systems, which is what this is all preparation for. So we'll come back and look at emergence in the complex systems and why complicated versus complex matter and so on. Okay, see you in the next podcast.